Guys, I'm gonna give people till about 6 to show up and then I will go ahead and do intros anyway. And then Damien, you've been here, you can attest, sometimes SWOC can be kind of a late arriving crowd.
I can concur.
All right, sound check one more time because I was having problems with the computer and didn't hear any of you.
We're good.
We're good. If you guys can hear me, I can hear you now, so we're good.
Perfect.
I can hear you.
All right.
Rep the hail badge.
That's right. Just right there.
Put it right there. Join at all times. Anybody come to boot you out of that room?
Nope. All good.
Not bad.
I can share my screen.
I just wanted to come back over, make sure everything started at 6 like it's supposed to. And then I will go watch it at home. There.
wonder if we can get our videos to go today. That'd be nice.
Oh yeah, definitely. 'Cause this is slides and not the
Yeah.
I changed my mic input. Y'all can still hear me okay?
Yep, you're good.
Okay.
Yep.
I'll do this as a quick welcome to those that are in attendance and those that are online. I know we have a watch party at our Curry campus, and I know we have we also have a watch party in here as well as people watching on our live stream. So welcome to all of our audiences, and thank you guys for coming back. Braden, Lucas, Damian, I know you guys were able to make the trip down with some of your other colleagues in March when we got to do this live, but we appreciate you guys having an opportunity or having time and making time in your schedule to visit with us again and go over it for those that were unable to stream and unable to join us remotely that day. We are very grateful today to have members of the OSU AIAA capstone teams here talking about their various rocketry projects and solar plane projects. Yes, I'm a solar physicist, so I am a little bit biased towards solar plane, but these things are the way they are. We are glad that they were able to join us again, and we will be, of course, recording this as well as streaming it. So we hope that as you get a chance to watch, if you have questions, I'm monitoring the stream, and there are other people that are monitoring the stream as well. If we get questions, we will pass them along to the presenters. And so if you have questions, feel free to type them in the chat, or if you're in your venue, our watch party venues, just get them to me as you can, and I will make sure to pass them along. But without further ado, I will turn it over to you guys. I'm not sure which one of you wanted to start, but I will let you guys make that decision.
Yeah, thank you so much for the introduction, and we're of course happy to be back. If y'all do have questions, feel free to interrupt us. We'd be happy to answer them either during the presentation or after. So we are OSU AIAA. We consist of 8 different aerospace teams here at Oregon State University. And today we're just going to kind of go through all of them, talk about what we do, and I guess let's just jump right in.
Sweet. Well, hello, everybody on the other end who I can't see today. I think, I don't know, it's super cool to be back talking to you guys even virtually, because for those of you guys who weren't there with us last time, I made an introduction for myself because I remember what it was like sitting in those same chairs that you guys are probably sitting in today, because I was a graduate of SWOCC. I went through their mechanical engineering program. I was part of SPEAR. I was part of that research team, and that's ultimately what led me to jumping into AIAA. And now I am the team lead for one of these teams, the High Altitude Rocket Team, or HART as we call it. Next slide, please. So essentially what we are is one of 3 rocket teams on campus. However, we all have different goals, different accomplishments that we'd like to achieve. We have 2 big ones that our team specifically wants to shoot for. One of those being a final altitude goal of 100,000 feet. I think last year's team really set us up good. We had our first fully successful launch and recovery that the team has ever seen before last year with a peak apogee of 64,000 feet, just short of Mach 3 as a top velocity. So that really set a good ground for this year's team to come in and try to establish a pattern of consistency. And the best way to do that is to kind of divide and conquer. We are one big team, but progress is better made as a combination of these 4 sub-teams. So we have aerodynamics, avionics, propulsion, and structures. And just a little sneak peek, I want to show you guys a video, if we can get that to play, as to what this team is all about. So I don't know if we had audio there, but it doesn't matter.
David, you may try, if you're sharing the screen, you may try to share it and make sure you click the share audio as well.
I don't know. I think it was just background music. There wasn't, I mean, there was some cool explosions, but it's all right. So that's essentially what we're doing is we design, we build, and we fly a 2-stage rocket. Just happens to be the only 2-stage rocket on campus and one of the very few in the Pacific Northwest alone. Designing comes in the first phase of our capstone class in the early parts of the year. That first probably 3 months is dedicated to design, and that includes details from last year. How did they succeed? What do we need to do? What do we need to change? All of that sort of thing. And then we move into manufacturing. We had some pretty cool stuff come up this year that was new, but it was also reiterations of last year. So the ideal timeline for one of these things is what we start with, what we call subscale. What this is essentially a tuned down version of what a full scale flight would look like. We don't fly 2-stage, but we do fly a dummy sustainer, or the top stage is what we call it, that mitigates that basically copies the weight of what a full second stage would look like, so that we can test ejections and we can test that separation. That is what makes a 2-stage a 2-stage. And then we move into what we call boosted dart. Now, this is essentially what the full scale airframe is under. It's the same airframe as a full scale. We fly, again, 1 motor and a second stage. This allows us to test propulsion, whereas a subscale is dedicated to our avionic systems, because as previous timelines have shown, avionic systems finish up first. We want to get them initial testing prior to throwing 2 big tests into one flight, essentially. So we don't want to fry avionics if propulsion goes bad. We don't want to lose, multiple thousands of dollars in propellant if our avionics don't work. Assuming all of this goes according to plan, we move into full scale finally, which is where we should be right now in the calendar. Essentially, this is where everything has to come together to make one final flight. We're not quite there yet, but we will be. I think this year there's been some things that have come up that are going to limit us to flight 2, but it's still good, useful data for future teams to come in and look at and reiterate on and make that final flight happen earlier next year. So yeah, that's kind of what we shoot for towards the end. This is full scale final flight in May last year was what hit 64,000 feet. Next slide, I think. So this was a brand new sub team that we introduced this year. This is a new sub team that we dedicated solely to aerodynamics. Last year and years prior, this has kind of been a thing that our structures team has taken on, but we had one of our new capstone guys come in this year, and he had some preliminary knowledge on how CFD works, and he saw enough work to be done to make this a dedicated team. So essentially what they're doing is all data analysis. They sit behind a computer, run CFDs on previous launches, try to figure out what exactly is going to get us from that 64,000 feet to the 100K goal that doesn't have to do with new propellant, that doesn't have to do with, maybe it is weight reduction. But part of that was fin design. So we based our new fin design this year solely on these CFD analysis, these simulations that they're running. Weight reduction, we integrated 2 fully composite motor tubes into our builds this year. And then we also added this, what we call a pitot probe, which is essentially what allows us to monitor dynamic pressure, which just gives us a lot more data to fall back on for future teams to come in. This wind launch correction kit was a new idea that a different capstone had in mind when he came in. He was new this year. Essentially what this is a ground station, a big box with a 30-foot pole and a computer linked into it that monitors live feed from local weather stations, which would allow us to basically throw our launch angle at whatever is the ideal launch angle at that day, at that time, to maintain a perfectly vertical flight, because we've had, launches in the past that have landed 8 miles in a horizontal direction. If we can correct that, that would be amazing. And then surface finish, this boils down to paint and wind tunnel testing and all sorts of things. So that's all new tasks that a brand new sub team has integrated this year. Super cool stuff that we haven't done, but we can utilize it for just about every other team. So next slide. How do we recover? So a big part of our builds falls back on successful recovery. We don't just want to launch a rocket in the sky and never see it again. We want to recover it, and that's how we get our data for new builds. So this is our avionics team. You can see a little picture up there on the right. Small group, but that was the early part of the year. So they design what we call an avionics bay. This is a 3D printed assembly that houses all of our computers, our mag switches. These pictures that you can see with these circuit boards are mag switches, which allow us to basically kick on our computers on the launch pad once the rocket is fully integrated and it's inaccessible on the inside. We run a magnet around the outside of the body tube to cue our computers to start, because if we leave them on for prolonged periods of time, batteries will die. We won't recover data. So that's kind of their whole thing. They integrated a couple of new computers this year. Post-launch tracking is kind of what this entire system is all about. So next slide, I think. Okay, yeah, so propulsion. We are in the middle of running simulations on new propellant, but every single propellant that we run in a full-scale build is done in-house in a lab that we have off of campus. All of our propellant mixes and chemical formulas and all of that stuff is passed through, chemistry instructors here on campus, faculty advisors that have knowledge on previous teams that we weren't a part of, that sort of thing. So we're always experimenting with what's going to get us that higher altitude, because propulsion is what obviously, makes your rocket go up. So when the team first started back in 2016, we started with this propellant mixture called liquid sand. And then we moved to this black flame, which is what we are currently using right now. These are pretty similar, with the exception of grain size in ammonium perchlorate, which is the one oxidizer that really makes this stuff go. So super dangerous stuff, but if it's done safely, it's super fun. And then we're studying this, we're studying this new propellant called cherry limeade with a new AP that shows on our simulations shows a higher specific impulse value than anything we've ever used before. Burns at a much higher temperature, but specific impulse is basically a measure of propellant efficiency. So that's kind of the number that we're focused on the most when we're trying to idealize propellants in both of our stages. Next slide, I think. And then the airframe, this falls back on structures. So if you're looking for more of a hands-on experience, this is definitely where you want to be. Instead of sitting behind a computer running calculations most of the time, or just studying. Structures is responsible for 90% of our full airframe manufacturing. So that includes these fins here. These discs that you see in the top right corner are what we call a bulkhead. These were CNC'd by 2 students in AIAA this year. they're part of a different team, but they have a machine shop in their garage that allows multiple teams to go in and utilize their resources. So these bulkheads basically integrate into the rocket, into the body tube, and they're secured by screws on the outside of the body tube that allow us to secure our motor tubes inside without worrying about, the tube sliding forward or backward in the body tube. Because if you have a rocket go up and the tube is pushing forward, it's going to try to slide into your AV base and stuff like that. So we want to secure them as tight as possible. Fin manufacturing, this bottom left picture that you can see is where we actually attach our fins to the body tube using a epoxy resin with a fillet. And then this bottom right photo is a picture of us doing our finalized designs for, or finalized manufacturing for composite layup. So this entire body tube and these fins are all carbon fiber. So that requires a lot of post-processing to, cure the epoxy in the carbon and make sure it doesn't just peel off when we apply it. So that is structures.
All right, I can take it from here. Hey, everybody, my name is Lucas. I'm on Hale. I'm a second year electrical and computer engineer here on AIAA. And moving forward from one of the three rocket teams that Damien mentioned, if you're interested in the aero flavor of aerospace, we have two plane teams on AIAA. And so the first one up here is Design, Build, Fly. Fun fact, this was actually our first team for AIAA. It was founded, I think, about 12 years ago. As the name implies, the competition for this team is to design, build, and fly a remote-controlled aircraft from the ground up every single year, according to a new set of challenges and goals that are provided by the competition heads. For example, last year's competition was all about high thrust and short takeoff and short landing. So you saw a lot of planes with pretty beefy motors on them. They could pump out anywhere like 120 amps to them. And then you had high lift wing configurations. In addition to short takeoff and short landing, they also had to fit within a parking space. So not just the aerodynamic considerations, the power considerations of your plane, but also how does it work operationally on the ground. And so when they had to fit within a small parking space, what our team did is they built folding wings. And so they would fold them up when they needed to park, and they could deploy them for takeoff and landing, and then the full flying of the vehicle. So looking at this year's mission, it was a mix of manual and autonomous flight. And so where this came in is they actually asked teams to build two independent aircraft. The first one was a mothership, which is the one you can see here, partially constructed in the photo, that would carry a smaller autonomous, payload, autonomous glider plane that would deploy in the air from the mothership, and then it had to autonomously land itself. So on one side, you have to develop a reliable and robust remote-controlled aircraft and train someone to fly it. And then you also have to do all this controls programming and autonomous understanding on how you're going to fly a secondary aircraft off of your main aircraft, which is super duper cool. As far as how they went about it, they constructed the plane custom. They were doing simulations on the airfoil and how the actual shape of the aircraft would come about. And then on the control sides of things, it had to fly using predetermined waypoints. So if you've ever messed around with the RC plane hobby, there is open source flight computers out there that allow you to interface with GPS and IMU and orientation data in order to have your plane autonomously navigate airspace and fly as it goes along. And so that was the technology they were implementing. In addition to the central technical challenge, every one of our teams is very much invested in the community. And so when we talk about getting hands-on projects in the hands of students, that's something very important to us. And that's not just college students, that's people that are in K through 12 or people in local high schools or areas or people that are prospective students. And so DVF was a big part of our outreach this year. They were interfacing with a lot of elementary schools locally in the area, teaching them a little bit of aerospace and what we do on the teams. Next slide, please. Oh, thank you. So just taking a quicker, more detailed look at the mothership this year, they went for a 70-inch wingspan and 2 dual props. There were pretty beefy motors on it. They spec'd it for 10 pounds of payload capacity. And then while they didn't have to make it autonomous, it just had to be remotely controlled for the mothership versus the fully autonomous payload, they did integrate their autonomous circuitry and platform into it so they could fly it autonomously if they wanted to. And then, I don't know if here this video will play. Watch that. This was them in the very beginning. A fun thing is you can't just show up and build a plane for the first time and hope that it works. And so they had a variety of off-the-shelf glider kits and powered planes that you might find in a hobbyist store that they were buying in order to understand what goes into building an RC aircraft. And so this is one of their more successful test flights with that styrofoam plane. As far as the construction of it, it was majorly made out of basswood and balsa wood for a lightweight airframe so they can have a high thrust to weight ratio. And then when it comes to manufacturing and design, we have a lot of facilities on campus that allow them to laser cut all those components. In the bottom left corner, you can see that waypoint mission planning I was talking about. That's PV Field, one of our fields on campus here, that allowed them to play with that technology in developing their aircraft.
And a fun fact about that video that you just saw is that was their first successful autonomous landing of the glider. So that thing landed by itself, which is pretty cool.
All right, and so that's design, build, fly. It's one of our two-plane teams. Moving forward, our agricultural drone team. This one's sort of an interesting one. It turns out that there's a problem in Thailand where the farming population is aging out. So farmers are becoming more elderly and it's harder for them to maintain their farms and their fields. Just physically, it's much more difficult for them to go out there. And so a farmer connected with Oregon State University with this problem statement and asked them to come up with a solution that would allow these farmers to still produce the output they need on their farms and do everything that they've been doing their entire lives despite their aging condition. And so our agricultural drone team was born out of this research grant partnership. The idea behind it is you can have a heavy lift drone that will be able to autonomously navigate a farm and deploy things, anything from water to pesticides to herbicides to seeds, which allows this platform that can do a lot of the manual labor that is involved in farming. And so the past couple of years that this team has been working, it's been a lot of design work, collaborating with the customer. And then this year they were putting a lot of those designs into action, physically assembling the drone, and then doing a lot of validation, a lot of controls programming, breaking things, fixing things, and very much taking on that engineering process that is involved with that. Overarchingly, in addition to, thank you. In addition to developing this platform bed, the most important components to the customer was that it would be open source, and inexpensive. So the idea is that you can put this technology out on the market for not a lot of money so that any number of people could replicate the design and use it without having to front a lot of cash in a situation like this. This here is a video of them, one of their first successful flights with the drone to a 20-foot altitude. Some previous mishaps with some of their drone propellers and the control system had caused the drone to actually flip over in some initial tests. And so this was one of the first ones where they're getting pretty excited that their platform was actually working with a payload on it, and it was looking very, very stable. As far as the images, I can talk a little bit more, sorry. As far as just a little bit of features that they built into the drone this year, in addition to the core functionality of autonomously navigating field, they also wanted to make it more user-friendly. So you see things like a Raspberry Pi on board that allows you to update a mission physically to the hardware of the drone, and then you can boot that information off the Raspberry Pi to get the drone to fly autonomously, as well as some safety features like object detection and avoidance, as well as a return home function that allows the drone to return if it detects that it's low on battery, or if the user has lost visual line of sight of the drone, they can press a button and the thing comes back safe and sound. So that's agricultural drone. All right, awesome. This is the second one of our rocketry teams. This is the one that I'm on here. I'm sporting Hail merch today. This one is our biggest team by far, and it is our high altitude liquid engine rocketry team. So as compared to a solid propellant, liquid propellants, there's a lot more fluid dynamics that you're dealing with when you have fluids, in this case, like liquid oxygen. For our oxidizer, you have cryogenic fluids to work with, and it becomes a very complicated, very difficult process. When you see things like the space shuttle or SpaceX rockets, these are all liquid bipropellant rockets. And so we're trying to do something similar to the real space industry just here out of Oregon State. Next slide, please. Awesome. So just an overarching goal of what we're doing, we intend to design, build, and launch a single-stage liquid bipropellant rocket to the von Karman line, which is defined as the edge of space at 100 kilometers or 328,000 feet. Taking a look, I'm going to quickly move through this because we got a lot of content here to cover, but quickly looking at some of our systems, this is what our subscale flight vehicle looks like. It is 21 feet long, and it features all the plumbing, controls, structural components, and our second generation engine that will allow us to fly all of our systems, hopefully to 30,000 feet this summer. On the left, you can see a P&ID, which is a piping and instrumentation diagram that allows you to kind of see from a higher level, abstract out what's happening liquids and fluids wise from the rocket. Next slide, please. Awesome. So one interesting challenge about liquid rocketry is, in addition to building an entire flight vehicle that you have to trust and work and not blow up on the pad, you have to build a lot of supporting ground infrastructure. So when we're talking about just like getting the propellant onto the rocket, we like see like Cape Canaveral and launch pads, there's so much infrastructure on the ground that allows you to safely and remotely operate your vehicle in preparation for launch. And so here at Oregon State, we have our horizontal test stand, which is on the left, and our vertical test stand, which we're currently developing for the full vehicle. The difference between the two, the horizontal test stand on the left was built first. It's just for static firing, just the engine. And so our first generation and now our second generation engine have been hot fired on it. If you see an image, the bottom left cylinder looking shape, that represents the engine. So it's a very small component of it. And then everything behind that is just to safely operate and fire the engine. On the right side, the VTS does everything that the HTS can do on top of supporting a fully stacked flight vehicle. So we have clamps that will hold down the rocket to allow us to static fire the engine with the fluid and plumbing aboard the subscale vehicle, as well as serving as a mobile launch pad trailer. So the whole thing's on a 30-foot by 10-foot trailer that we're going to take down to LA on I-5 and launch east in the desert. Next slide, please. And so this plays sort of a cheesy hype video we have of what we're doing. Awesome. So looking at that, that was the first static fire of our second generation engine. It is the first and the second liquid engine developed by college students ever made in the state of Oregon. So here are some stills of the second hot fire there. But this is the difference between our first and our second generation engine is a 50 to 20 pound difference in how much it weighs for the same thrust output. So one is a proof of concept, whereas the other one is actually light enough that we can put it on the flight vehicle this summer. Next slide, please. Awesome. So we're composed of 6 sub-teams. I'll run through this as fast as I can that enable us to do every component of this. And when we talk about hands-on work and what students actually do, it's on these sub-teams. First up is propulsion. Propulsion developed Mirror 1, our first generation engine, as well as Mirror 2, which is the flight-ready one. In this middle here, this table is actually pulled from Wikipedia. It's kind of cool. We use a pintle injector, which is the bottom left photo there. It injects an annular flow of fuel, and then in all the directions and the holes you see on the side is liquid oxygen that gets pushed out into that ring flow to create a cone of mixed fluids. And we are one of the pintle injector rockets that you can look up on Wikipedia. They've been developing this engine for the whole duration of this program. It's been going about 7 years. And now this year, we're very excited to actually put it on a rocket and send it up. For the vertical test stand, I already talked a little bit about this, but this team is completely dedicated to the design, fabrication, and operation of the vertical test stand. So this year, they've been doing a lot of welding, manufacturing work. They have to support the tanks for our gaseous nitrogen that pressurize the entire system, as well as all the fluids, plumbing, and control to get our propellants, our liquid oxygen, and our kerosene to the rocket. On top of that, you see the massive launch rail there. The thing's, I think, about 60 feet we're speccing right now. And so they have to build all the support structures for that miniature launch pad to support the rocket lifted before a launch sequence. Our fluids team is at the very heart of the plumbing of what's making everything happen. So you have an engine, but you need to get your propellants from point A to point B to support that engine and combust it in the chamber. And so on the vertical test stand, we have a little more space to work with. We have some larger pipe runs that we can work with. But on the subscale vehicle, as these bottom two images show, you kind of cramp everything into a very, very small space. So this is a lot of computer-aided design on their part, as well as still maintaining a very safe and operable fluid system for the combustion of the engine. For structures, they're all about putting the whole thing together. So we run an aluminum airframe. So you can see in all of these images, but especially the bottom one, we have a mix of structural tanks that hold our liquid oxygen and our kerosene, as well as wider, like the three-fingered structural component you can see in the bottom left of the image that physically wire and harness everything into the rocket. And so they're doing a lot of FEA structurally validating that this can take the forces that the rocket's going to produce, as well as talking a lot of cross sub-team collaboration on how you can get your fluid system rigged up, and then the wiring in the same part, and then how can you deploy a chute, and how does that all come together in assembly. So they're very fundamental to the actual rocket when it comes together. Then we have air and recovery. They do exactly what it sounds like. They are the aerodynamics and recovery team. So any aerodynamic surface on the rocket, they deal with a lot of simulation on their part, making decisions about the nose cone shape and the fins and stability for the rocket, as well as designing a recovery system. So we have a 2-parachute system. Like Damien was mentioning, where you have a drogue chute and a main chute. Our drogue is 15 feet in diameter, so it's already a pretty big chute, but that's the smaller one, just to slowly descend from 30,000 feet. And then when we're close enough to the ground, we pull the main chute. Why we don't pull the main chute all the way to the top is we don't want it floating like 30 miles by the time it hits the ground. So that makes a very hard recovery on our part. And so it's a 2-stage parachute system, and they're doing all the force calculations, the snatch force when we actually pull at apogee, and making sure that whole thing is up to the standard that we need it to be safely. Then avionics, I can talk your ear off about this. This is what I'm on. Avionics is at the heart of the controls. Any electrical system on HAIL, that's what avionics deals with. So it's not just that lovely looking flight computer you see on the right. It's also all the pressure sensors, the thermal sensors, the solenoids, the limit switches on both the on all of our electrical systems. So horizontal test stand, vertical test stand, our subscale vehicle, as well as a smaller subscale vehicle. And so we do a lot of validation, custom in-house electrical work. Because we're doing so much active fluids control, we need a lot more custom design components because we need to interface with so many more sensors. And so that's a lot of things that we do on avionics. And then that's all of HAIL. So I'll pass that off to Brayden for APOP.
Yeah, so moving off from one of the rocket teams and on to one of our jet propulsion teams. So APOP is actually a design competition where every year a team is given, or teams are given this little JetCat P100 engine. You could hold it in your hands and you have to design some sort of object that goes onto the engine and performs a specific task. So last year, the design was to generate a reverse thrust mechanism, which you'll see here in a sec. This year, their job is to design a variable thrust nozzle for this engine. So, as you can see here, the way that they sort of went about it this year is by designing fins that are all connected together by a helix gear, and a servo motor inputs motion onto one of the fins, which controls all of the fins at the same time. So you can adjust the amount of thrust that the engine is producing by changing the flow out of the nozzle. And the team is actually at competition right now at Edwards Air Force Base in Ohio, which is pretty cool. So this team sort of runs, this is, oh, my bad. Got to mute this video here. This team runs in the fall and the winter because their competition takes place in the spring. And during the fall term, there's a lot of, designing what is this mechanism going to look like. Here is a video of a very early test in the late fall. And then during the winter is when they actually do a lot of the manufacturing. So on the previous slide, you saw a couple of iterations of their nozzle. And then in the spring, they go down to the competition. There's a final report. And, I guess in a week or so, we'll find out whether or not they won the competition. But last year's competition actually won first place, which was pretty cool. But that's APOP. Moving on to solar airplane. So this is a research team. And the goal of this team is to design a high altitude flying glider that is completely powered by solar panels. So if you think about satellites, they'll go up into space, they'll do their science research for a couple of years, but eventually they die out. And then you just have space debris in the atmosphere. At the professional level, these gliders can stay in the air for months at a time. They have very low emissions, they have very little launch costs, and they can perform the same science research that some of these satellites can. So last year, you can see a little rendering in the top right here of what our solar airplane looked like. It's got a huge wingspan. It's a lot bigger than it looks. But this year, the team made a dual fuselage because they found that when you attached a payload onto just one fuselage, it created a lot of buckling and flight. And so they added a dual fuselage. And the goal was to increase the payload capacity while also increasing the flight time. So last year's team was able to achieve a 2-hour flight time. And this year's team wanted to achieve that same goal with a dual fuselage design. So we have a test flight video here. Doesn't have some sound. Oh, my bad. I'm skipping through these slides accidentally all the time. Right. But here you can see a test video. We go out a couple miles away and we have this guy named Dave, and he flies the plane for us. He's like a professional drone pilot. For DBF's plane as well, he can also fly that plane. But I think this is super cool, just a casual glider in the atmosphere flying over unknowingly passerby cars. So I don't know. I think that's cool. But that is solar plane. Moving on to our last rocketry team. This is the student competition rocket team. So you've already heard a little bit about the other sub teams. On the other rocketry teams, we are no different. A lot of the stuff that we do is very similar, but I want to highlight some of the really cool, unique things about this team. So first, up in the right side of the screen here, you can see BEAVS, which is our blade extending apogee variance system. Now, our rocket is part of an international design challenge, and every year we go down to New Mexico. It's called IREC, and we compete with other schools in different categories. So our rocket that you saw on the last slide competes in a 10,000-foot apogee category, meaning we have to design a rocket that gets as close to 10,000 feet without going over. And this that you can see here playing in the video, it will use a PID controller to detect the altitude of the rocket as it's accelerating up to the 10,000 feet, and it will deploy these air brakes, or these little thick pieces of metal that induce drag on the rocket and slow it down to approximately 10,000 feet. So if we aim for just over 10,000 feet, then this can decelerate us so that we reach as close to 10,000 feet as possible and ideally win our competition. So this is the second year that BEAVS has existed. I think it's really cool. Additionally, we kind of just like to have fun and optimize our geometry as well. We do a lot of FEA on some of our internal structural components, as well as our bulkheads. We try and make those as efficient as possible from a mass perspective. We've also got a CubeSat payload. This is what I did my senior design capstone project with. So we launch a payload into this rocket, and each year you're free to do whatever you want for the payload. And so this year, our payload was a planetary exploration mapping and data analysis system, PEMDAS. So the idea here is that if you were to go explore a foreign planet and it's got some sort of potential habitability for life, then what would you want to send to that planet to determine if there's life there? And so our payload has an assortment of sensors that collect data while the payload is descending down. Once the payload gets on the ground, you can see here in the picture on the right, there's a little scooper mechanism that will scoop dirt into a repository, and then it'll analyze the material composition of the soil. We've got a little camera on the bottom so that while the payload is descending from the rocket, it'll take pictures of the terrain. And then we've trained an AI model to identify features that would correspond to indications of life. So like rivers or trees or things like that. And so that's some of the things, those are some of the aspects of this payload. Now, that was all 7 of our teams. At this point, I think, I don't know, we can open it up for questions, but that's all we got. So thank you guys. I'll go ahead and stop sharing here.
All right, thank you guys for, everything. I actually have a couple of questions from me, and then I'll keep an eye on the stream, and if there's anybody here that has questions, but one of the things that has come up as far as, with my experience with students is, the questions I get are, what should they focus on to be able to do things like the types of things that you're doing to get them prepared for being part of a capstone team or part of a volunteer rocket team, or however they wish to go about it? What kind of coursework, interest things should they be looking at, or how would you recommend they get started on things if it's something that they would be interested in?
Yeah, well, I think all 3 of us are going to have the same answer here, and that is you actually don't need any prior experience at all, at least when it comes to our teams, and I'm sure that's the same at other colleges as well in their aerospace programs. I mean, I don't know about Damien and Luke. I'm sure they started in a similar place as me, but I had like 0 engineering experience at all. No aerospace engineering experience, nothing. And what you need is just passion. You just need to have an interest in that stuff. People show up to our meetings all the time with, just like me, they didn't have any idea about how to do any of this stuff. And we just teach them how to do that. I got taught how to do stuff. I started off with Hail and then I transitioned over to Skirt. And so you really don't need any prior experience. All you need is that interest and dedication as well. It does take up an extra, chunk of time depending on how active you are in addition to your classes. So as long as you're passionate and you're willing to invest time into learning and teaching yourself and getting that experience, then you don't need anything else. That's all you need. I don't know if anybody else has opinions.
Yeah, I'll add on to that. I guess what I want to mention is it's very easy for new people to feel overwhelmed when they walk into a meeting, especially a few of our bigger teams that have a lot more to them to succeed. People walk in halfway through the project all the time and they're like, why am I here? I'm like, because you want to do rockets, like it's not as challenging as it may seem. And the reason for that is because a lot of what we're doing is recorded. We record every ounce of documentation that we have done since the beginning of all of these teams, but there's no reason to feel behind, or you got a lot of people there that are ready to catch you up on whatever interests you. And up until your capstone year, you can put in as much or as little time as you want. It's common to say that these teams don't expect anything out of somebody if they're just volunteering, but we love to see that, because that's what keeps these going, is people like you guys who will eventually, some of you, come up to Oregon State and have these same interests. That's what we try to fall back on. And that's why we're doing this presentation, is to get this out there, because being an alum from SWOCC, I had no idea until my 3rd year in the fall that I had no idea that AIAA was even a thing, that AIAA gave us the opportunity to form this chapter in the college. And the second I found that out, I was in meetings all over the place. I was like, I'm in, let's do it. And then I landed on Hart. So
I appreciate
Yeah,
that.
I won't. Oh, well,
Appreciate
I
that.
won't reiterate what they already said. All the same stuff. Just sharing a small example on my 2nd year here at Oregon State, and everything they said is absolutely true. I showed up last year. I've been on Hale for a year and a half, almost 2 years now. Know nothing about rocketry at all. I played with some RC planes when I was a kid, but that's about it. And now it went from me trying to dedicate time out of my schedule to learn more about this, and now I want to take time out of everything else in my schedule to spend more time on these things. So it's addictive. It's fun. If you have the passion for it, that's all you need.
Yeah, I know we have kind of the same experience here with our Spirit team, to where we get into students just coming in volunteering on stuff, and the next thing you know, they're working more hours on that than on homework. But we try to avoid that, but we understand the way things go, because you get passionate about things and then you lose track of time, which is one of the fun parts of it. I think one of the things I did want you guys to talk about, because I know we brought the Spear team up and we crashed one of your AIAA meetings early in the year, and I know you guys had talked a lot about your industry partnerships and industry connections. So how do you guys work the projects and then connecting to helping the students get from OSU out into industry?
Yeah, well, one of the pros about, or one of the benefits about the fact that we've been around for 12 years is that we already have former OSU AIAA alumni in a lot of, the popular or even unpopular startup aerospace companies. So that's sort of it's sort of a connection already. But even if those connections didn't exist, there are other things that we do. So, we host career events where we recruit local companies in the Pacific Northwest, aerospace companies, to come in, give presentations, network with students. But like, I'd say the main thing, honestly, is that it's kind of rare to be able to get hands-on aerospace engineering experience in college. So when a company sees that on somebody's resume, or when a student gets an opportunity to talk about that at an interview, it just like blows them away. It's a really unique thing to have. It's a really unique tool to have in your tool belt. So that is what I would say is the biggest contribution to students getting hired to these companies for jobs or internships.
That's definitely important, because I know trying to, it's about the education and it's about the educational process, but it's also about starting the career. So it's a very key avenue for it. We'll look through the chat to see if we have any more questions. I did have one other one that's unrelated to the academics thing, but Damien, you've mentioned it twice, but what is this cherry limeade thing? I know it's a propellant, but why did it get to be called that?
That is a great question. I do not know the exact answer. It is not a drink. I don't know. They all have interesting names. Most of our propellants come from a combination of research with BTS Space. They have a YouTube channel. It's great. Check it out if you haven't already. Combinations of that alongside old chemistry instructors here that have watched these teams grow and can validate the mixtures for one. But I guess not necessarily to answer your question about how it got its name, but the reason that we are working with it is, like I said earlier, one of the biggest considerations when we are trying to decide a new propellant comes with specific impulse. Every single propellant, based on mixed chemistry, based on what chemicals are involved and how much of what, it's like baking almost, except it's a lot more complicated and dangerous, is that decides what your specific impulse values are, what your burn time is going to be with a mass introduced. I don't know. Like I said, one of the biggest things that we consider is that ISP value. The larger the ISP, the higher the propellant efficiency. And that doesn't directly translate to a prolonged burn time. Maybe, being a two-stage, our ultimate goal is a rapid acceleration in the booster to reach a higher peak velocity at the time of separation. But once we're there, we want a prolonged burn time in the sustainer to reach a max altitude. So we want to spend as much time as possible at as high of a speed as possible. And there's a kind of a fine line there. So it's a combination of both cherry limeade and this black flame that we also mentioned that would involve that larger burn time. So it's got a lower ISP, but it has a higher burn time, lower acceleration, but a longer burn overall. So it's kind of a game of cards where you kind of got to just, plug and play, kind of figure out what you want to do. And that's why we do test fires. So, obviously when we are doing these propellant mixes, our true launches are not the first time that we burn this propellant. We do test fires similar to hail, but it's a static fire at the airport on a test stand that we built ourselves. It's not as fancy, but we also don't have all the bells and whistles that a liquid engine does. So,
That pretty much
answer your question?
It's always interesting about the different types of propellants and the different challenges and different parameters on them all. We did have a comment on the live stream from our Spear Fearless leader, Crystal Hopper Myers, who said, "Thank you guys for coming back." And she's sorry she wasn't able to be here in person, but she was glad that we were able to broadcast this again for students that didn't get to see it last time. And we'll also have it archived so that we can share it with our future engineering classes and physics classes that will be able to see it. So we're glad to continue being able to help share aerospace engineering and help kind of promote you guys' program as well as we move forward. I did want to ask if you guys had any specific contact information that you wanted the students to have, or would it be easier just for them to contact us and route it to you guys, or how do
We can share our website. All of our contacts are on there.
Yeah, so I'll go ahead and post a link in the chat here. And while I'm at it, I might as well just show you as well. So we do have a website, and if you go to somewhere, you can, let's see, I don't even remember how to do this, but there's, yeah, okay, scroll to the bottom, typical sign up thing. No, this is not it. Does anybody know where it is? There's a
Yeah,
contact.
if you go to the about us, I think is where it's at.
This is it.
Maybe.
Oh, sorry, my bad. Yeah, contact us right here. If you contact us, you fill this out. It goes directly to our club web email. Our club email is also just aeronautics club at Oregon State. So I don't know, anybody can feel free to screenshot that, but this is the email that it goes to. You can also just feel free to send us an email there. But either of those are our methods, and I'll post this email in the chat as well.
There's also pages for each of our respective teams inside of that have contacts for specific leads and people that you're trying to reach.
We appreciate that, and if students have further interest and further questions that they send our way, we will route them to you guys. Thank you guys for your time today, and we do appreciate it, and we hope to see you next time we're up in Corvallis, and hopefully we'll bring students along with us.
Yeah, of course. Thank you guys so much for having us.
All right. Thank you guys. Have a good rest of your day.
You guys too.
You too.
See you later.